Okay. Fresh start. Quarter 3, semester 2. We're over halfway done with the school year. Time flies when you're having fun in geometry. All right, we are going to get into the next lesson in chapter 5. If you don't remember where we left off before the exam, because it does feel like a while ago, we did lesson like 5.1, 5.2, and then you guys did a little quiz over those two. And there was only 2 problems on the semester exam with the chapter 5 stuff, the last 2 problems. So we're going to continue our journey in chapter 5. All right, so as a little refresher, I like this warm-up. It says, construct the following triangle centers. We're not going to do it like with compasses or anything. We're just going to kind of like sketch this. So who can remind me what makes up the circumcenter? The intersection of what? Tyson? Nice. Perpendicular bisectors. A perpendicular bisector of each side is 2 things. It bisects it, meaning it intersects at the midpoint, and it's perpendicular to that segment. All right, so again, we're just going to kind of sketch this. I'm going to start with my bottom side of this triangle and just kind of guess where you think the midpoint would be, probably about here. And then just notate like, yeah, we're approximating, but it's the midpoint. We could be more exact if we got out a ruler and stuff like that, but all right, so the perpendicular bisector is perpendicular to that side. So I'm trying to get it to cross at like a perfect 90-degree angle. That's kind of my goal here. And goes through the midpoint, something like that. It doesn't have to go from the vertex to their side. Mine kind of looks like that in this case. That is something different. That's an altitude. We'll get to that in a second. Perpendicular bisectors does not necessarily stem from the opposite vertex. All right, my second side here, let's try to find that midpoint. And then try and draw a perpendicular segment. So something like that would look like it'd be perpendicular and bisects that side. And then the same thing with this last side. Now I know we're not doing this perfectly, but if you do it semi-correctly, they should all cross in one point. And that right there, folks, is your circumcenter. The intersection of the perpendicular bisectors. Good, good, good. Okay, moving on to incenter. That's an intersection of what? That's orthocenter. Yes, so. Somebody other than Tyson. Jessa. Angle bisectors. Angle bisectors. Okay. So again, we're just going to approximate this from each angle. If you have a straight edge, that will help. If not, it's okay. I'm going to do this pretty free-handedly. You're going to try to draw in each angle bisector of each angle. So you want to split it like directly down the middle. That's what bisect means. Splits in half of each angle of the triangle. And again, if you do this fairly accurately, they should all cross at one point. Inside the triangles, incenters always are located inside the triangle where the angle bisectors intersect. Okay, that's what we talked about in 5.1. In 5.2, I gave you two new ones. I'm having a hard time talking to you. 2 new centers, the centroid and the orthocenter. Okay, anyone remember what the centroid is? An intersection of what? You just shout it out. The medians. Good, the medians. And a median, folks, a median is from a vertex to the opposite side, intersecting at the midpoint. Okay, so again, let's just start with this side right here. Let's try to find the midpoint. The median would be from the opposite vertex to the midpoint. It's not perpendicular necessarily. It can be, but it's that line that goes through the midpoint. All right, I'm going to do this side next. Find the midpoint. So the median would be from the opposite vertex connected through the midpoint. These are the ones that I made you find on the coordinate plane fairly accurately by finding the midpoint of one side and then finding like this segment length that went through the vertex, through the midpoint of the opposite side. That's your centroid. That is where the triangle balances. Okay, and then somebody said altitudes earlier. Altitudes is the orthocenter. And an altitude is kind of similar to a median, where it goes from the vertex or the opposite side from the vertex, however you want to think of it. But it's perpendicular to the other side, not passes through the midpoint. Okay, so if I start up here and I want to draw the altitude, I'm trying to find the perpendicular or like the shortest distance from this point to that side. So that one is fairly kind of straight down. You can tell it's not necessarily the midpoint, but there would be one altitude. I'll do this one next. From this vertex, I want it to be perpendicular. So sometimes I kind of like to do this too, like just to get a little like sketch of where it should come in at. So it looks like it's fairly perpendicular. Something like that. And then same thing for the last one. From this vertex, perpendicular. So I can see right here, that'd be my orthocenter. Okay, this lesson doesn't really involve those, but we still need to know them moving on in chapter 5. And 5.3, the lesson we're going to do today, it's pretty short. 2 big ideas for the day, and it's not too bad. A couple vocab words we need to review over before I throw these theorems at you. First of all, you know what the word like equality means in like real life, like equal rights. In math, the symbol for equal or for equality is this symbol right here, the double bars. We know it means equal. And it's 2 or more things with the same value. The reason I say things, I don't love the word things, but it can be numbers, it can be variables, it can be a lot of different things in math that have the same value. So if I said x equals 7, or the measure of angle A equals 60 degrees, I can show those 2 values, the measure of the angle and the angle measure, have the same value by putting an equal sign in between them. Okay, inequality, that's what kind of comes into play today, are symbols like this where you have like is less than, is greater than or equal to, or even equal sign with a slash through, which means it's not equal to. These are all examples of inequalities. And the definition here is a comparison of 2 or more values that are not equal, not necessarily equal. I'm just going to put our not equal. So, for example, if you have like x is less than or equal to 7, like it could still be 7. 7 is less than or equal to 7. It's equal to, but not necessarily like always equal to that. Could be less than or equal to. Anytime you see the word like inequality in math, you're thinking one of these symbols. It's going to involve one of those like greater than, less than symbols. Okay, that's just a couple vocab review. Theorem review that we talked about earlier. I don't remember what chapter. This is chapter 5 or chapter 4. I can't remember. Is if that we have an exterior angle of a triangle. So an exterior angle is any angle that's formed by like one side and an extension of the other side. So angle 1 here would be an exterior angle of this triangle. We talked about how the measure of that exterior angle is the same, is equal to the sum of these 2 remote, is what we call them, interior angles, or non-adjacent is another way to say that. So it's the same as the sum of the measure of angle A and the measure of angle B in this case. Those 2 interior angles that are not touching it. Okay, really quick review why this works. In the green triangle, folks, angle C and A and B have to total how many degrees? 180. They're inside a triangle. This plus this have to total 180 degrees, right? Now, angle C is also supplementary with angle 1. So angle 1 and angle C have to add up to what? 180. So obviously whatever this is, that's going to be the same as these two angles put together. Their sum. Okay, that's why that theorem worked. We went through and did like a little proof of that. So here's the new, kind of like an extension off this theorem a little bit. It's called the exterior angle inequality theorem. And it's saying that the measure of any exterior angle in a triangle is always going to be greater than those two remote corresponding like angles. Okay? So in this case, you can see I have triangle ABC. Angle 1 is considered an exterior angle because it's made up of this side BC and an extension of this side. So from the exterior angle theorem, I know the measure of angle 1 is the same as, in this case, the two remote interior angles would be A and B, the ones that don't touch or make up angle 1. I know that the measure of angle 1 is going to be the same as that sum. So what this theorem says is that, hey, if these angles added together total the measure of angle 1, then that exterior angle has to be greater than each individual angle. It has to be greater than whatever the measure of angle A is. And it has to be greater than whatever the measure of angle B is. Okay, now this makes sense. And careful here with my differences between the greater than symbols and the angle symbols. Okay, that says the measure of angle 1 is greater than the measure of angle A. That's how I read that out loud. This makes sense because obviously if you add two angle measures together, you're always going to get a sum that's bigger than the angle itself, right? The only maybe like counter example you could kind of think of, you're like, oh, well, what if I had 0 degrees and 100 degrees? Then this would be 100, but could we have a measure of 0 degrees in a triangle? No. Or somebody might be like, ooh, what about if I had, sorry, that kind of jumped weird. Oh my gosh, I don't know why it's jumping around on me. Sorry. Maybe you're thinking, oh, what if one of these is 100 and then I have a negative 20 degrees and now this is 80 and that's not greater than 100, but can we have negative angle measure in a triangle? No, so there's really no like counter example you can come up with. You can't have a 0 degree angle in a triangle either. So that's kind of why this makes sense. Obviously, whenever these two added together, angle 1 is going to be bigger than each individual angle. Kind of make sense? It's one of the big ideas for today. Okay, let's try an example problem with this. Use the exterior angle inequality theorem to list all of the angles that satisfy the stated condition. I want to know the measures that have angles that have measures less than the measure of angle 4. Okay, so angle 4 is right here, and sometimes it helps students to kind of like trace the two sides that are making up this angle, or the two like rays. So one of the rays is this extended side of this side, and the other side is this triangle. So it's an exterior angle to that triangle I just traced. Angle 4 is an exterior angle to that triangle. So this theorem we just talked about says the measure of angle 4 has to be greater than the measure of angle 1 and the measure of angle 2, since those two angle measures total the measure of angle 4, their individual measures have to be less than whatever that exterior angle is. Okay, that's the big idea for today. Let me ask you this question. Looking at this like other triangle right here, is 4 technically an exterior angle to that triangle? It's not, because it doesn't lie on any side of the triangle. It lies on like the extension of two sides. So remember, one of the sides like has to be the side of the triangle, like this one. And the other side can be an extension. That's what makes an exterior angle. But do you see how it lies on the extension of both sides? Not an exterior angle. Angle 5 would be an exterior angle to that green triangle, okay, because it lies on this side, the extension of this side, okay, so just be a little careful with that. Sometimes that can be confusing on these ones where they have a couple triangles in the diagram. This one's phrased a little different. This next one says, I want you to find angles whose measures are greater than the measure of angle 7. See how we're doing all these comparisons here? Okay, angle 7 right here is an interior angle. It's inside a couple triangles. I could say this triangle. So I'm looking for exterior angles that are going to be greater than angle 7, which is an interior. So I look here, and if I extend this side, I see angle 9. Angle 9 has to be greater than 7, and what other angle? 6. Yep, the 2 remote, okay? 9 has to be greater than 7 and 6. So one angle that has to be greater than 7 would be 9. I don't know about 6 and 7. I don't know their comparison. I can't make any assumptions based off of that exterior angle sum. Okay, then I see 5 is also an exterior angle of this red triangle. 5 is greater than what 2 angles? 7 and 8. Right, 7 and 8. Those are the 2 remote. So 5 would also have to be greater than 7. Okay, this is tricky to see, but technically 3 is also an exterior angle. See that? Like I said, sometimes it helps people to like trace it too. Angle 3 is technically an exterior angle. 3 would have to be greater than 7 and 8 as well. So measure of angle 3 is greater than 7. Okay, that one kind of went backwards where it gave you an interior angle. Last one. Find angles with measures less than the measure of 9. Okay, so I'm trying to figure out where 9 is an exterior angle for. So definitely this small triangle. We just talked about this. So 9 has to be greater than both 7 and 6. So the measure of angle 7 and angle 6 would both be less than 9. Just based on that little triangle. All right, angle 9 is also an exterior angle for like this big triangle. Agreed? Shares a side with like this side right here, an extension of the bottom side. So 9 is greater than 1. And these 2 angles put together, 2 and 7, well, we already said it has to be greater than 7, so we just need to add in it also has to be greater than 2 then. Because obviously if it's greater than their sum, it's going to be greater than each of those. That would be it. Okay, yes?
Could you also put measure of angle 8?
For 9?
Yeah.
Oh, technically yes. But they only want using the exterior angle inequality theorem. Yeah. Yeah, I see what you're thinking here. You don't need to go that far. Okay. I want you guys to do this one. Using the exterior angle inequality theorem, list all the angles whose measures are less than the measure of angle 14. My hint to you is that there are 4 angles that you can say that using this theorem. See if you can find the 4. All right. I first looked at this small triangle. So looking at that triangle, what two angles does 14 have to be greater than? Good. 4 and 11. These two. 4 and 11. And then the other triangle, that 14 is an exterior angle for, would be this big triangle, where it extends that side. So it also has to be greater than which ones in this case? 2, and then the sum of 3 and 4. We already said 4.
At this time, middle school
So
wrestlers
3.
can be released to get ready to load the bus. Again, middle school wrestlers, I need Telecutting and Eaton Chapel to the office, please. Thank you.
Okay. Is 14 an exterior angle to this triangle? No. No, it's not. The only side it has is this extended side. It doesn't share any other sides of the triangle. Not an exterior angle. Okay. Any questions on that one, folks? Okay. The next theorem I think is even easier. It's kind of fun. And this one says if you know the length of the sides of the triangle, you can make some comparisons with the angles across from those sides. Okay? So if one side of a triangle is longer than the other side, then that angle that's across from the long side, so like here if I look at XY they're telling me is 9 units. And then they're telling me YZ is only 7 units. So if I look at comparing those two sides, YZ is greater than, or sorry, XY, the red one, is greater than YZ, the blue one. So this theorem says that same comparison is going to hold true for the angles across from those sides. So in this case, the angle that's across from XY is Z. The measure of angle Z is also going to be greater than the measure of angle X, since X is across from the smaller side. Now think about why this makes sense really quick. Let's say I'm forming a triangle with my arms this way. So I have a side that connects my fingertips, okay? So do you agree that the smaller the angle I make with my arms, the smaller that side right here is going to be? Right? And then the bigger that angle, the longer the side. And think of a right triangle. What's always the largest angle in the right triangle? Okay, the hypotenuse is the longest side. What's always the longest angle, or sorry, the biggest angle? 90, the right angle. It's always across from the largest side, which is the hypotenuse. Okay. This also works in the converse. If you know comparisons of two angle measures, like in this photo right here, I can see the measure of angle J, which is 110 degrees, is definitely greater than the measure of angle K, which is 45 degrees. If you know that for sure, we can't just say, oh, it looks bigger. It has to be marked. Then you can say the side across from angle J, which in this case is KL. That side would be greater than. We don't know exactly what the measure is, but it would be greater than JL. The side across from angle K. Isn't that cool? Okay, so those are two theorems, relationships in triangles. that we need to know. Let's try a couple of these and then we're done. List the angles of triangle ABC in order from smallest to greatest. All right, so I see a scalene triangle here. No congruent sides. What's my smallest side? AB. AB is my smallest side. So my smallest angle is going to be C. We want to cross it. Okay, I'm going to do smallest to largest. So my next smallest will be side BC, which means angle A. So always want to cross from it. Would be the next smallest. And then my longest side, AC, will be across my largest angle, angle B. That's really it. All right, we're just going to try 2 more problems. This one says, use a figure to determine the relationship between the measures of the given angle. So here's my picture. They want me to compare the measure of angle BCF. I'll trace that in blue. BCF. They want me to compare that to the measure of angle CFB. CFB would be here. All right, so I'm looking at those angles. I can kind of mark them too. This one and this one. I'm going to mark them differently so I'm not showing they're congruent. So BCF across from that angle is a side length of 15. And across from angle CFB is a side length of 14. So is this angle going to be greater than the red angle or less than? Is the blue angle going to be greater or less than the red angle? Greater. It's across from 15. Greater than 14, right? See what I'm thinking there? Okay. Thank you, whoever answered that. I don't know who that was. Next one, DBF and BFD. All right, looking at my first one. DBF. DBF is across from a side measure of 5. So I need to compare that to the angle across from a side length of 12. Or you can think this symbol's got to eat the bigger number. So 12 is my bigger side there. So that one should be less than. Guys, if you don't remember how to read these symbols, because I'm not kidding, when I tutored students in college, some of them got these confused. It's okay. This one, open it up, it forms an L. You read that as less than. Less than. It forms an L. Less than. Or you can always think it eats the bigger number. So this one, if it's eating the bigger number, that says greater than from left to right. Okay. This time we're given angle measures, and they want me to determine a relationship between the side lengths. So RP, they want me to compare to MP. Let's take a look at those sides. RP is across from an angle measure of 70. That side. MP, that side is across from an angle measure of, how can I find that angle?
180 minus 60 minus 80.
Good, they all lay on a line. So 180 minus 60 minus 85. I think it's 35. 35, yep. Okay. So, RP across from the larger angle is going to be the larger side. Make sense? RP is across from the angle of 70. That's going to be a longer side than across from the angle of 35, which is MP. Okay, last one. RQ, which is across from the angle measure 30 degrees. How can we compare that to PQ? And you can't just say, oh, PQ looks like it's longer. No. That one's across from an angle measure of 85 degrees. So PQ would be the longer side, meaning RQ would be less than PQ. That's it. Not bad, right? Wow, you got some homework time. Let me pause my recording quick.